maybe you could like start recording. Okay, it's already recording now.
Yes.
Right.
So I guess I first want to say thanks everyone for attending. I really appreciate it. I know we kind of got started a little bit suddenly out of the blue, and there were typos with the scheduling and all that, but we're here now, and that's great. So yeah, so if there's any questions or anything throughout the talk, or if you can't see some element of my presentation or something, please just go ahead and unmute yourself and just shout out. Just shout it over your mic, and we'll see what we can do about that. Yeah, so today I wanted to talk about B-matching games, but not really like too much about the games themselves, but more about them as this example of when you can compute the nucleolus on graphs of bounded tree width. So this talk is, I wouldn't say it's super deep, but it is broad in the sense that like we're going to be connecting a few different areas. We're going to be connecting like cooperative game theory and the computation of a classical object known as nucleolus with some congruency constrained optimization and with some formal models of dynamic programming and with like graph decompositions into tree decompositions. So we're going to show how all these things kind of link up and how they can be used to give this theorem that on graphs of bounded tree width, one can compute the nucleolus of B-matching games in polynomial time. And indeed, this could extend probably to many other different games. This is sort of like an example. Like for many different games on graphs of bounded tree width, we could apply similar techniques. So we're going to start off by introducing the nucleolus for those that are not familiar with it. Just kind of like motivate what this object is and why people in cooperative game theory care about it. And then based on a technique that was pioneered by Kostya Pashkovich, many people probably know him in this group, he applied to weighted voting games this technique that reduces the nucleolus to a congruency constrained optimization problem that is naturally related to a cooperative game theory, which is the minimum excess coalition problem. And we'll see what all this stuff means as we move on through the talk. The next section we're going to be talking about is how congruency constrained dynamic programming is essentially efficient. Like if you have a dynamic program for a problem in this sort of formal model we'll describe later, then you can lift that to a congruency constrained version. So essentially you can add a congruency constraint to this dynamic program, and you don't lose much in terms of the complexity of your problem. Then we'll talk about B-matching games, and then we'll apply this sort of technique, this sort of strategy that we're outlining in 2 and 3 to B-matching games to compute the nucleolus on bounded tree width graphs. So let's start by considering the nucleolus. So what's going on here? Cooperative game theory itself studies the division of a surplus like between collaborators. So you have some kind of shared resource or something, and everyone's working together to sort of achieve some kind of profit or like net some kind of value. We want to kind of know how do we distribute that value amongst the contributors based on how much they contributed to the problem in some sort of fair way. So when we're defining a cooperative game, we define it as an ordered pair n with this value function nu here, and n is just like your player sets, and this value function it takes as its input subsets of the players, and essentially it outputs like how much that subset is worth, how much value they can generate. And the sort of main type of objects that we're trying to find in cooperative game theory are imputations. These are a subclass of what are called solution concepts, and they're essentially vectors in dimension number of players that tell you ways to share the surplus. So like the ith index of this vector would be how much of the surplus the group generated I should receive payment for. And we want 2 natural things here for this imputation. We want it to be efficient, and what this means is that the entire surplus is exactly what is shared, right? So if we look at what the entire group, all n of them, can generate together, that is exactly what is shared amongst all n of them if we sum the entries in every position in this vector. That's what this shorthand kind of means. And we also want our imputations to be individually rational. Now, What this means is that each player should receive at least what they could earn on their own, right? So for a singleton coalition of that player, they should be paid at least that much. Right? This is just so that the players have some sort of incentive to be involved in the group rather than striking out on their own. Now, we want to kind of go beyond this, and we want to think about more than just imputations. So we can look at this individual rationality sort of concept, and we can start thinking about, well, what happens if we try to extend this to coalitions of larger size? And we might initially want that for every coalition S, the payoff X to that coalition would be at least the value that coalition could earn. But that's rarely possible. I mean, it's possible in some interesting cases, but in general, it's not possible. So a nice kind of compromise we can make is we can look at the coalitions which are worst off, and we can maximize the difference between, we can sort of like maximize maximize their deficit. So make them as well off as possible. So if we look at the excess, which is a quantity that is like the payoff to the coalition minus the value it could earn, we want to sort of like maximize this quantity for the worst off case. And this can be accomplished by a linear program. A linear program is what we call here the least score LP. And what it does is it maximizes epsilon. Epsilon is going to be tracking this excess, right? So epsilon is bounded by the excess of each particular coalition. In particular, it's bounded by the bottleneck excess. And then over here, we also have constraints that say that our X should be an imputation, right? So X is efficient and it's individually rational. And just a little bit of notation, right? We call this the optimal solution to this least score LP, epsilon 1. And if we look at the set of imputations, the set of X vectors for which X with epsilon 1 is feasible for the least score LP, then these are the points that we call the least score. These are the imputations where this bottleneck excess is maximized. So this is great. This is kind of building on the stability notions that we were generating earlier with the imputations. This is something that is, in some sense, more stable because more coalitions are doing better in least score points than they are in just general imputations. But we want to go further. So we want to say, well, we stopped at the minimum excess, but there's bottlenecks above this. Like there's coalitions that are second worst off, there are coalitions that are third worst off, and so on. And what if we could find an imputation that that optimize all of these excesses in some sort of like sensible order? And that's what the Nucleolus is doing. So formally what we mean is, if I was looking at some kind of imputation or maybe even some kind of least score points, then I could collect all of their excesses in a vector, right? That's what this theta X is. It's a vector where the entries are running over these subsets of players, all the subsets of players. And it's taking a look at their excesses. So each entry is the excess of a coalition. So excess minus nu of S. And you're going to take those excesses and you're going to sort them in a non-decreasing order. So the worst ones are at the front and the best ones are at the back. And the Nucleolus is the unique object, I'm erasing things, is the unique object which, unique imputation X star, which lexicographically maximizes this theta vector. So what that lexicographic maximization means is it's looking at the worst off coalition, it's going to maximize that. Subject to that, it's going to maximize the excess on the second worst off coalitions, and subject to that, the third worst, and so on. So intuitively, you could think of this as the most stable possible imputation. It's kind of like, it is, again, because it assigns like the most unhappy people the best thing you could do, and subject to that, the second most unhappy people, and so on. This object was originally defined by Schmeidler in 1969, and since then it has proven to be this classical object of study in cooperative game theory, competing essentially with the Shapley value, the other sort of classical object that everyone is interested in. In Schmeidler's paper, he proved many properties of the nucleolus. One was that it is a unique object, which is not necessarily obvious from this definition, but it is unique. And he proved some other interesting things. They're not really relevant here, but for example, he showed that the nucleolus is a continuous function of your value function. And there's lots of applications. So this thing is certainly earned its place in cooperative game theory. For example, all the way back in the Babylonian Talmud, which is the sort of book of laws in ancient Babylonian society, Ullman and Maschler actually discovered this. They found out that there's this procedure for bankruptcy division when like a king dies and his wives have to like share his estate. And they sort of found out that this rule that was in this book for how they distribute his estate is it sort of follows the nucleolus actually of a natural related cooperative game. And there's many more modern applications. For example, like shared water supply management, fair file sharing in peer-to-peer networks, resource sharing in like job assignments, and airport pricing. So for example, like if you're at an airport, there are many different airlines that are flying out of your airport. And some of them are big, some of them are small, and they all have different kind of utilization of that resource. And the question is like, how much do you kind of charge them for space at your terminals in a way that is sort of fair with respect to their utilization of the airport runways and the resources there? So this can be modeled with the nucleolus. So our interest as algorithm designers and combinatorial optimization folks is to compute this nucleolus object. And we want to compute it in a way that is efficient, and that kind of depends on how you are going to encode your cooperative game. So for example, we don't usually think of these cooperative games as being encoded by a function, by an explicit representation of the value function, because that would be writing down an exponential number of values, one for each coalition. You usually want to think about games that have some kind of compact representation. Maybe instead of this explicit specification, your players are vertices in a graph or something. And the value a subset of vertices earns is maybe like a maximum weight matching on the induced subgraph, or maybe it's the weight of a spanning tree, or maybe your players are, I don't know, a ground set in some matroid, and your value function is actually your rank function. There's many different ways you can think about these things, but you want some sort of compact representation that is like polynomial in the size of the players, and we want to think about computing the nucleolus on that object. Now, the sort of gold standard for computing the nucleolus is Maschler's scheme. And this computes the nucleolus by a series of linear programs. So we go P1, P2, all the way to P large N. And the ith linear program kind of looks like this. So this thing is defined recursively. So at first you need to know like what are the imputations in the previous linear program, what are the things that optimize the previous one. And then amongst those imputations, you want to look at the coalitions that were not made tight by the previous linear program, and you want to optimize their excess. So we start with the least score, right? And then if you're thinking about what P2 might be, you'd say, look at all the least score points. And then you would say, amongst those, look at the second bottleneck excess and optimize that, right? So, but you may notice that there's a little bit more here. There's this span we put in front. So what's happening here? Well, if we didn't have this span, if we had just ran over the tight coalitions, well, the problem is that in each round it's possible, and actually there are some papers that show this, it's possible that only one coalition goes tight in every round. And so that would lead to an exponential number of rounds. And we want to avoid that. So that's why we put this span in front. And it says that coalitions that are formed as like a linear combination of tight coalitions, we also want to exclude those from this thing. And what that does is it ensures that this n here, this number of linear programs, is controlled by the dimension of the underlying space, which is the number of players. And so that's how the master scheme yields a linear number of LPs, at most n, and the final LP is going to have a unique optimal solution. That's the termination condition, and its unique optimal solution is going to be the nucleolus. Okay. Are there any questions about that? Does that make sense? Or is that kind of clear? I know it's a bit of like a crash course on computing the nucleolus, but if there's any questions, please feel free to interrupt me. Let me know.
Sorry, I have a question.
Great, thank you.
So this, for all S not in the span, so you're really optimizing over the remaining degrees of freedom? Is that the rationale behind it?
Yeah, exactly. Okay. There are essentially some coalitions that have been fixed in previous rounds despite not being tight, and we want to avoid those.
Okay, cool.
Great. Any other questions? No? All right, well, if you think of something, feel free to stop me. What we're going to do now is we're going to think about how to reduce the problem of computing the nucleolus to the problem of finding a minimum excess coalition in your underlying cooperative game with respect to some imputation, plus one congruency constraint. So this technique was first used by Pascovich in 2018 in the case of weighted voting games. There was sort of like this problem with the way that weighted voting games nucleolus was being computed, and there's sort of like this series of papers in the literature trying to figure out what its complexity was, and Kostya kind of like was the one who actually gave the final like correct pseudo polynomial algorithm for weighted voting games, and he used this technique to reduce it to a congruency constrained optimization problem. So if we look at the separation problem, I mean in the ellipsoid method sense, for PI, it looks like this. You want to look at the excess of the given x vector that you're trying to separate over, and you want to find the coalition of minimum excess. So that's that minimum excess coalition problem we're talking about. Now, if you're just doing the least core, these constraints don't appear, and so the problem just looks like this, right? Given some vector x, find a coalition with minimum excess. But in general, for the ith iteration, the ith round of Maschler scheme, there's also this spanning tight set we had from the previous round that we have to sort of eliminate the coalitions that could appear in there. So the first thing you might do is you might fix a basis of this spanning set, right? So let's fix a basis B, and say, well, all right. Now we just need to find vectors that aren't in the span of this basis. We didn't do too much, but then Pascovich comes with this lemma, and this is a really nice lemma. And if there's time at the end of the talk and there's interest, I'd be happy to show the proof of it, because the proof is really quite beautiful in my opinion. It's very elegant. If we have this set P, and sorry, oh God, there's a lot of P's that show up. But if we have this set capital P of prime numbers, and there's a certain number of them, if there's at least log of n factorial of these primes, then a set of vectors V is going to be linearly independent over R, if and only if there is a prime number in this collection P, such that V is linearly independent over the finite field FP. So why is this nice? Well, this is nice because it lets us reduce this linear independence question over R to a linear independence question over finite fields, which sort of enables us to do some enumeration. So using this lemma, we can see that instead of working over the span of B, we can enumerate over the P's in this collection, and we can then look at the span of the basis over that particular finite field. And of course, over here, I've mentioned some things we're glossing over, right? We can find this basis B in polynomial time. That's something we can do. It's technical, don't worry about it. We can find P in polynomial time. The prime number theorem guarantees that if we just check the first like n cubed-ish numbers, then we can actually find the primes in there and it'll work out. But again, technical stuff glossing over. And using Gaussian elimination, we can find a basis for the orthogonal space in polynomial time. So all these linear algebra questions, let's just push them to the side. All these prime number questions, they're doable. But let's continue with this reduction. So we've gotten ourselves down to checking coalitions that are not in the span of a basis over a finite field. And we want to sort of keep going, keep pushing this idea. So now let's look at a basis of the orthogonal space over some finite field. And now we can enumerate even more things, which is nice, right? We can look at this basis. We can run over the vectors in this basis, and we just now need to require that our coalitions are not equivalent, not like 0 modulo this prime, right? Because if your vector has some non-zero inner product with a vector in the orthogonal space, then you definitely don't lie in the span of the original space, right? So now we're sort of simplifying this problem more and more. And the last thing we just want to do is we want to enumerate the ways that this can happen. And basically there's like p-1, right? Different things that this could be if it's not going to be 0, 1 up to p-1. So now we're enumerating over the primes, we're enumerating over the vectors in the orthogonal space, and we're enumerating over the non-zero elements of this finite field. And then we're just saying minimize the excess of a coalition subject to a single congruency constraint that says that the inner product of this vector with this the instance vector of this coalition is k modulo p. Oh, Shra, you can just interrupt me.
Yeah. Okay. So what's the notation for v? Like, do you mean it's just x?
Oh,
the vector.
Right. So what's going on over there? The thing I'm just
yeah.
Well, I mean, so what I'm actually meaning here is take the inner product of v with the 0, 1 instance vector of this S.
Okay.
Does that help, or is there still something there?
No, that's. I just didn't understand the notation of v when you.
Okay, good.
Can you just go like one slide before this and
This way?
So you fix a basis and then you're looking at, and then you look at the orthogonal complement, and then you're looking at vectors in that span, right? So there's an X and there's a V. So I guess V is.
Right. Yeah. Sorry. There's an X, and there's a V, and there's also a nu. So it's a bit. It's a bit tricky there.
Okay. Cool. Yeah. Thanks.
Sure. No problem. Right. So what have we done? Well, we've reduced this problem of separating over a particular round of modular scheme into this problem of just being able to compute a minimum excess coalition subject to one general congruency constraint, modulo a prime. And it's important this prime is of a size that is like polynomial in the number of players in terms of its value, or its unary encoding, if you will. So yeah, that's just kind of summarized in this theorem. And all it says is what I just said. If you have a cooperative game and if I have some prime polynomial in n, like if I could design an algorithm which solves that minimum excess coalition problem subject to that congruency constraint for any particular imputation, for any particular vector in this finite this like finite field vector space, and for any scalar in this finite field. If I can do this in some time t, then I can also compute the nucleolus of that game in time t paying, this is kind of like just a rough upper bound in n6 factor on that enumeration. So in other words, like to compute the nucleolus, it suffices to compute to solve like this congruency constrained version of this min excess coalition problem. So that's kind of what we're going to focus our attention on is when is this minimum excess coalition problem? When can we solve the congruency constrained version easily? And dynamic programming is going to be a candidate class for that. So the idea in this section is to realize that if a problem can be solved efficiently with dynamic programming, so could its congruency constrained version. So let's take a look at how that might look. So here's an example for the knapsack cover problem, right? So we can consider n items, and each of these items has some price. Say that price is xi for the ith item. And each item also has a weight, ti, and we have some threshold t. And we want to find a collection of items that has weight at least t. And we want to do that at the minimum possible cost in terms of this x value. These knapsack cover problems can actually be derived from a very important game. It's this weighted voting game that Pashkovich actually computed the nucleolus of. In these weighted voting games, each player has a weight, and a coalition can earn a value of 1 if and only if their total weight beats the threshold. Otherwise, they earn a value of 0. So it's essentially meeting a certain like majority required to like pass a vote or something, but with different numbers weighted differently. And so if we're looking at this problem here, well, we can design a dynamic program for it. And here's how we do that. We're going to let d of k and u denote the optimal solution to this subproblem, which is to minimize, again, the price of the items in S, subject to S now at least U as opposed to T, and using only the first items. And yeah. So we can write a recurrence for this, and that recurrence might look something like this, where to solve dku, we can look at either what happens if we take the kth item or not, right? So if we choose not to take the kth item, then that would be looking at k-1 items. We still have u threshold to go. Or if we take the kth item, then we have attained a weight of wk, and we've also paid a price of xk for that item. And then here's just kind of like analyzing the base cases, right? Either you pay x1 if that item alone can admit its threshold in the case where k equals 1, and otherwise the problem is infeasible, so we pay infinity. Now, this problem, this knapsack cover thing, we can add a congruency constraint, and we can increase our complexity by by an amount bounded in the prime. So now if we look at a prime P, right, a vector V and some target congruency Q, then we can look at this this knapsack cover problem subject to a congruency constraint. And it's the same problem. Again, you have items and you're trying to meet a threshold and you have a price to pay for that. But now we say that our final knapsack that we're covering with, it has to meet a certain congruency modulo P. And we can take our dynamic program from before and we can modify it in a way that turns out is actually like very principled, that is actually a way that works in general. And we do this by adding another index here, if you will, that tracks the congruency of our subproblems. So now our collection of subproblems have this form. It's using the first k items, meeting a threshold u, but now having a congruency for the items we've picked so far to be m. And we can write a recurrence for this as well. So again, down here are our base cases. Infinity if you're not feasible. If we're looking at the first item and it meets the threshold and it meets the congruency, we can take it to pay for it. Maybe other corner cases, but what's important here is this recurrence. So again, we have the cases, if we're not taking the kth item, then we just have to look at the k-1th items, the first k-1 items, and try to meet the congruency and meet the threshold with them. Otherwise, if we are taking the kth item, then using the k-1 items which remain, we have to meet the threshold minus the weight of the kth item. And we have to make a congruency that is m, but it's shifted by the impact that the kth item has on the congruency, right? So we have this vector v, and if we look at the kth item in it, that's going to impact this by a value of vk modulo p. So this allows us to, essentially what we've done is we've taken a dynamic program for this minimum knapsack cover problem, and we've added a congruency constraint, and we've extended the dynamic program to account for this congruency constraint. And all we've paid is a factor of p, essentially, for our prime, for those like p new indices for this, that this thing can run over. And now, if you recall from earlier, we had that the primes that we're interested in for cooperative matching games or cooperative game theory in general, those primes are polynomial in size in terms of your number of players. So that's an acceptable factor of increase in our setting. So what we want to start thinking about now is, well, we want to look at what happened in this weighted voting game, and we want to sort of formalize it, sort of say, what was the principle behind what happened there, and what can we like sort of like extract a general theorem on lifting congruency constraints for dynamic programs. And to do that, we're going to need some sort of like formal definition of what a dynamic program is. We all kind of have like an intuitive definition of what happens when you're doing dynamic programming, but it turns out there's actually a fair bit of literature on like formal models of dynamic programming. And the one we're interested in is this model by Campbell, Martin, and Rardin. And what they did is they said, you could think of dynamic programming as having a directed hypergraph object. And what you mean by a directed hypergraph is that each of your arcs has this notion of like what a source vertex might be, and it points towards all these other sync vertices in the arc. So it's a one-to-many directed arc, and you can think of your solutions to your dynamic program as finding a min or max depending on your objective sense. So let's say min. So finding like min cost hyperpaths from the source to the leaves. And what a hyperpath is it's, so you want it from the source of leaves. So you want it to start at a source and you want it to end at leaves. And each vertex in the middle, it should be covered. So for example, a hyperpath, if it took this edge Z, then it would then split and take this edge over here from C to EF and this edge from D to G. And that's one possible hyperpath from A to the leaves in this graph. The other possible hyperpath is to follow y and then take one of these two arcs, either from B to E or from B to F. So essentially, every time you have a hyperarc with more than one vertex, this path is kind of splitting and forming multiple subpaths below it. Right, so our solutions to our problems are going to correspond to hyperpaths that start at the source and at the leaves. And if we're trying to think an analogy to what we did before with writing recurrences, then the nodes in this hypergraph, so like A, B, C, etc., D, E, F, G, these each correspond to one of our subproblems, right? So in our weighted voting games, we had subproblems that ran over K, taking the first K items, and U, meeting a threshold of at least U. And each one of these nodes would correspond to one of those subproblems. And what the arcs describe is, the arcs describe how the solutions to these subproblems are obtained from the smaller subproblems. So if I'm looking at, say, like A, and I'm trying to charge a cost to the subproblem from A, which is actually the entire problem, then I'd want to look at the minimum of what happens if I stop doing that, if I make this decision Y, and then I solve the subproblem at B, right? Or alternatively, I could make the decision corresponding with this arc Z, and then I could combine the results of solving the subproblem at C and solving the subproblem at D into a single solution. And this is what's called the directed acyclic hypergraph model. And actually, Martin, Rardin, and Campbell showed that there is an extended formulation for minimizing the cost of hyperpaths on directed acyclic hypergraphs, an integral, actually, extended formulation. So it's nice. You can solve this with linear programming. You could also solve it combinatorially by essentially doing dynamic programming on this object, building up from the leaves the solutions to your subproblems and working towards the top. So again, if you think about our weighted voting game kind of running example here, let's look at this directed acyclic hypergraph. And it actually is a directed graph because each of our subproblems only doesn't depend on combining two subproblems. It basically takes one previous subproblem and adds an item or doesn't add an item to it. So we might have a node here for DKU, and there's two arcs emanating from it for the two decisions, either taking item K or not taking item K. And that leads us to two different arcs, right? Either the arc for the subproblem with one less item, same threshold, or one less item, different threshold. And you work down this directed hypergraph, getting towards the leaves, and then your paths in this thing reflect your solutions to this knapsack cover problem. And there's some subtlety here that isn't immediately obvious, but we can't just admit kind of like any dynamic program, anything that one might think colloquially of as a dynamic program. We want to have this property that every feasible solution corresponds to our original problem. So say every possible like knapsack of items that meets the threshold. We want all of these to correspond to some like source leaf hyperpath and vice versa. Each hyperpath in our graph should correspond to a feasible solution. We can make that correspondence formal, say with like an affine map between the two spaces or something, but for the purposes of this talk, let's just keep it on this informal correspondence level and you can look at there's a paper on this for more details, but let's kind of not focus on that. Let's focus on this subtlety right now. The knapsack cover satisfies this condition, but there's this other like kind of canonical example of dynamic programming. Some say like the Bellman-Ford shortest path, and it actually does not satisfy this property, which is good because otherwise we'd kind of be claiming that we can solve TSP, which wouldn't make sense. So just to sort of like dig into that, sort of comment a little bit. If we wanted to find a shortest ST path in a digraph, say maybe we're looking at this digraph over here, and we're trying to find a path, a directed path from like S to T, and we have some weights on the arcs, these 1s or these 10s, there's sort of some cheap arcs, some more expensive arcs. And we can sort of design a dynamic program, not in our formal sense, but in sort of like this more informal sense, based on this like recurrence, where if I had sort of subproblems that corresponded to a shortest path that used at most I edges and that started from some vertex, say Y, then I have kind of two choices. I can either not use my ith edge and just look at the subpaths that use at most I-1 edges, or I can look at all the edges leaving Y, and I can say they're leaving Y and going to Z, say one of them. Then I can look at the subpaths using at most I-1 edges from Z, plus the weight of traveling from Y to Z. So the thing about this dynamic program is that it absolutely works. Absolutely, it works. I mean, this is one of the most classical things in optimization. But one piece of structure it uses is that it doesn't have to worry about, in some sense, it doesn't have to worry about cycles because of like suboptimality, right? Because like I want to avoid situations where my paths take a cycle, but that would never happen because it's not optimal if we're just looking at like positive weights, say. But the thing is, as soon as you start adding constraints to this, that might break down, right? So for example, like if I was just to modify this, this recurrence and sort of transform it into a hypergraph, one sort of feasible thing I could do is start from the subproblem that used 4 edges and start from S and then move to A, then using with only 3 edges remaining, move to B, then move back to 1. So I formed a cycle and then move to T. Right, so this is something that is possible to take this kind of path here. Now, an optimal solution would never do this, but let's say we added a congruency constraint that said that the length of our path had to be 4 mod 4. So maybe we wanted like a Hamilton path or something. So we added a constraint like that. Suddenly what happens is that this path from S to A to B back to S and then back to T becomes an optimal decision for this this would-be dynamic program, but it's not actually feasible because it's not a path. Is that kind of clear? That's why we're adding this extra constraint when we're saying that we can lift dynamic programs to their congruency constrained versions. We're saying with the caveat that the dynamic programs, all their source sync hyperpaths, they map to feasible solutions. So we're not using any like structure about optimality to drop out solutions from the DP. Are there any questions?
I have a question.
Yes, thank you.
If you change the definition of feasibility to ST walks, then it becomes feasible, right?
Right, right.
But for some reason you're only interested in paths because you're doing dynamic programming.
Right. So if I'm interested in like the shortest if I'm interested in finding a dynamic program for the shortest ST path problem,
yeah,
then like there is this dynamic program of sorts that is designed by Bellman Ford, right?
Isn't this Floyd-Warshall?
Oh, perhaps, but
this is all pair shortest path, right? No, just ST. Yeah. Never mind. Yeah. Mm-hmm.
But yeah. Yeah, so you're interested in designing this dynamic program. And part of the correctness of this dynamic program is that it will avoid walks. On like say that everything's positive, it'll avoid walks. But as soon as you add a congruency constraint to that, this sort of dynamic program won't necessarily avoid walks anymore.
I see, okay.
so that's why we want to add this additional constraint that every feasible solution has a correspondence with a source leaf hyperpath, so that we're designing dynamic programs where when we add constraints, they don't suddenly start breaking feasibility. That's the idea. Thank you. I think that helped clarify it a lot, actually. That's a good question. Okay. So let's see how to extend what we did for congruency constrained knapsack cover to these more general hypergraph dynamic programs. So as usual, so let's just say we want to find hyperpaths in our directed acyclic hypergraph that have a certain congruency, okay? So we want a path, and this is just a shorthand I like to use for the paths in our hypergraph that are rooted or start at a vertex A. So we want a path from our source A that travels to the leaves in some hypergraph. So it has, A has these two arcs, and then it kind of blobs out down here into we don't know what. And we want to have this path, source to leaves, have this congruency V of this path to be K mod P. So, well, the paths from A can do two things, right? They can either go from F, in which case, right, P minus F is a path in the subgraph starting from D. And that we'd want that path to have congruency K minus this V sub F, the congruency of F. Now, on the other hand, if it uses E, that's where it gets slightly more complicated, right? So when it was using F, this is essentially the same as what was happening in the weighted voting games case, because this is just a singleton arc. But when you start looking at arcs that have more than one head to them, say B and C here, then it gets a little more complicated. So if this path P starting from A was to use arc E, then we would want this remaining object, P minus E, which is a path starting from B, as well as a path starting from C. It's the union of these two things. We want it to have, again, we want to have the same sort of congruency thing, but now we want that sort of congruency property to be a property that belongs to two paths when you sum them together. So the idea is a bit, I'll just talk you through it. It's kind of visual here. So if I look at, I again want to do this thing that we did before, where we took our subproblems and then we added another index that was tracking congruency. So in our case, we're going to take each node, say A, for example, and we're going to create a new node, AQ, that tracks the paths leaving A that have congruency Q, right? So we're going to do this for each vertex. So yeah, for each vertex, we're going, in the original hypergraph structure, we're going to create a new vertex. We're going to create P new vertices, and they're going to be labeled with some congruency, and it's going to track the subpaths of that congruency. So if we wanted to design this new subgraph, so we're moving from this original thing that I'm erasing into this thing over here, into this new directed hypergraph, and we wanted to track the paths leaving A that have congruency Q. Well, if we move along F, then we just need to look at the paths leaving D that have congruency Q minus VF mod P. But if we take E, suddenly there's a whole host of possibilities, because there's essentially like P different ways that that B and C could combine to obtain like this congruency Q minus V of E, depending on like, so if we just kind of run over the choices of congruency for B, right? So if B had congruency 0, the subpath from here had congruency 0, then we would want the subpath from C to have congruency Q minus V minus E. So if this one had 0, we want the subpath leaving C to take all the congruency we needed. But we could run this over everything, right? So if B had congruency 1, there would be another arc here, all the way up to like say B has congruency P minus 1. Then we want C to have congruency V minus Q minus V of E minus P minus 1 mod P. Essentially so that their subpaths combined have the congruency Q minus V minus E. And you have an arc for every possible way this can happen. Now, when there are only like 2 vertices in the head of your arc, that's fine. You only pay for P arcs. But what happens when there are arcs with like many outgoing vertices? We didn't forbid that in our problem, right? There could be like a large amount of vertices in some arc leaving a particular vertex. And then we'd have a lot of different ways to partition their congruencies. And that could be a problem. Say, for example, there's this arc leaving A and there's like M vertices in the head of this arc. Then you're going to create roughly like P to the M-ish new arcs. Less, but not much less, right? Not asymptotically. Different ways to sort of like form these congruencies. And if this M is not bounded by a constant or something, like if this M is genuinely like a function of the number of players, then you're exhibiting some sort of exponential growth in the size of your hypergraph, which is not a good solution. So before we apply this transformation, we want to ensure that the arcs in our dynamic program have a constant size. And there's a way to do that, actually. And the idea is kind of simple. If I wanted to take an arc that had like M vertices, then I could actually start constructing dummy vertices, and I could start linking up these smaller arcs as a path, as a path of where the arcs here are constant size. So if I had like A running from S1 to SM, that would make a new dummy vertex here. And I would have A running to S1 in that dummy vertex, and that dummy vertex running to S2, and dummy vertex that connects. Then there's S3 showing up all the way to SM minus 1 and SM. And because of the definition, like the way hyperpaths work, there is like an isomorphism between like the hyperpaths in these different hypergraphs. And all this does is like blow up your number of edges by a factor of the number of vertices. And after you do that, then you have constant size arcs, so that you can apply the previous transformation. And that'll give you a hypergraph object where the nodes can actually like track their congruency. Again, if there's ever any questions, just stop me. I'm happy to go back, happy to explain in more detail. So the sort of like construction that I just described, there's technicalities to it and there's subtleties when you actually go down to write the proofs, but in general, like the ideas are there. They're kind of like visual ideas, and you just have to sit down and sort of write them out carefully to make everything work. But essentially what happens is you get this result that says if I have some kind of combinatorial optimization or otherwise problem P, and I can solve it with a dynamic program, and that dynamic program is built on a hypergraph structure like H, then I can add a congruency constraint to P. If that congruency constraint has a prime modulus little p here, then I can solve this congruency constraint version in time O V E P cubed. Right. This is like a very rough upper bound. but again, you're paying for the size of the original hypergraph. You're paying for blowing up its number of edges into those paths, and then you're paying for enumerating the constant size paths. And the consequence of this is if we connect that with the work that we saw earlier on reducing the computation of the nucleolus to a congruency constrained problem, we can see that if we can solve this minimum access problem of a cooperative game, if we can solve this with a dynamic program in time t, then the nucleolus of that game can be computed in time polynomial in t. So essentially what this is done is it's given kind of like a general framework for computing the nucleolus. Like it certainly doesn't work all the time. It doesn't even work for all the known interesting problems that have polynomial time nucleolus algorithms. But it does work for some interesting examples, right? It works for this weighted voting games we saw. And it's going to work for the B-matching games that we're going to see. It's going to work for games on graphs of bounded Treewidth, which is an interesting class in its own right. So what are these B-matching games we're going to try to apply this result to? In B-matching games, you're given a graph, say G equal VE, and you're given some vector B, and what B does is it bounds the degree of the vertices in your underline, in the number of edges you can take. So we're also going to weight this thing, and then the simple B-matching game on G is a cooperative game where the players are the vertices, and your value function has the following sort of structure. It's the maximum weight of a B-matching on the induced subgraph. So you maximum weight some selection of edges from the induced subgraph on the number of players you're interested in this coalition, and that edge subset has to obey this degree constraint that says that the number of edges in M incident to a particular vertex has to be at most BV. In particular, this is what one might call like simple B-matching, because you can't take an edge multiple times. And commonly in B-matchings, you can take an edge more than once, but not in this case. So, I mean, for the case B equal 1, this was a long-standing open problem, recently resolved. And after that, sort of the next natural question is what happens with B-matchings? And it turns out that sort of like in contrast to how combinatorial optimization works, where in like classical combinatorial optimization, B-matching is like a very like, easy is not the right word, but like B-matching is also tractable, and it's sort of like you can reduce it to matching through like proper transformations of your graph. But in the case of B-matching games, in the case of cooperative games, the complexity of B-matching seems to be harder, and harder in meaningful ways than the complexity of matching games. There was this result by Biro, Kern, Paluzma, and I'm going to try Wojciechowski, sorry, and this fourth author, where testing least core membership is co-NP hard, even for the unweighted case, and all your B values equal to 3. And this likely means that computing the nucleolus of B-matching games in general is NP hard. Polynomial time algorithms in the literature, so what is known is that they rely on being able to separate over the least core. So when least core separation turns out to be difficult, it's unlikely that the nucleolus will be tractable. But this is actually an open question, like, is this actually NP hard? But it seems it's far more likely that it is, whereas in the B equal 1 case, there's a polynomial time algorithm.
Sorry, I'm a little confused. Why does co-NP hard imply NP hard, or likely imply NP hard? I mean, if it's co-NP hard, it's already a hard problem.
Right. So most like all algorithms in the literature for computing the nucleolus, they rely on being able to test least score membership in some way. So that means, that means that, well, there's no proof, but evidence points to it being the case that like the nucleolus should also be a difficult problem. Does that make sense?
Yeah.
Does that mean the Marshallus scheme, you can't use the Marshallus scheme?
Right, yeah, it means you'd have to come up with something else, because to compute, to implement Marshallus scheme, you would have to be able to separate over the least score. So given this complexity, we decided to study B-matching games with some structure, and we decided to impose the structure of bounded Treewidth. And it turns out if you impose that structure, then you can design a dynamic program for its minimum excess problem. And so then you can use that machinery we've just built up to compute the nucleolus. So I just want to outline that. So now we're going to be bringing in tree decompositions and Treewidth. So that's what I meant at the start of this talk when I said it was broad and that we're bringing a lot of like different areas here. So we have a graph G, and we want to construct what is called a tree decomposition. And this tree decomposition, it consists of a tree T, and it consists of a set of bags. These bags contain subsets of vertices from your original graph. And there's one bag for each vertex in your tree. And these bags need to satisfy some properties. So the first thing is that they need to cover the vertex set of your original graph. So if I union over all the vertices, all the bags I've created, then I need to have all the vertices in my graph. Another thing is that if I look at any edge in my graph, then there has to be some bag which contains both vertices of that edge. And lastly, if I look at a vertex of my original graph, and I look at all the, and if I look at the tree that's, or the graph, I should say, that's induced by the bags that contain that vertex, then that should form a tree. So all the bags containing a vertex, they're connected in this tree, and yeah, you could say that they're connected because you already know it's a tree, or you already know it's acyclic. So for example, I have this underlying graph here in black, and then these blue things, these are some bags you might form. And here's like kind of what the tree decomposition might look like. And there's this important parameter that is associated with tree decompositions. It's their width. And the width is essentially the size of the largest bag minus 1. And the reason there's this -1 for those uninitiated to the area, it's because it's so that trees can have tree width to 1. And the tree width, as a parameter of your graph, right, is the minimum over all your tree decompositions, the width of that tree decomposition. So the nice thing about tree decompositions is they can be made to be nice. So if a tree decomposition, so if we have a tree T, right? And it's rooted at R, and every vertex I in the tree sort of falls in one of these 4 types, then we can say that the associated tree decomposition is nice. And the classes are leaves. So leaf vertices, they have no children because they're leaves, and their bags have size 1. So there's like 1 vertex in their bag. There's also introduce vertices. These vertices have 1 child, J, and their bags have 1 more new vertex that they're introducing compared to their child. Forget vertices. Again, they have one child J, and their bags have exactly one vertex from their child's bag that is missing, that vertex V. So they're forgetting a vertex. And then there's joins. These vertices of the tree have two children, J1 and J2, and all three of them have the same bag. And it turns out that if your graph G has a tree width of W, say, then you can find a nice tree decomposition of your graph, and that will have width, the tree width of your graph times the number of vertices. And you can find this thing in time that is polynomial in the width times the number of vertices, so W squared times the number of vertices. So this is good. I mean, if you know that your graph has bounded tree width, then you can find a nice tree decomposition in polynomial time. And it turns out that you can actually do dynamic programming on these nice tree decompositions. And so we're going to see that now. But before I go on, I guess if anyone has any questions about tree decompositions or nice tree decompositions, now might be.
Just the tree width, the width is blowing up by a factor of the size of the vertex set. Isn't that bad? Like when you move to a nice tree decomposition.
Right.
Or is there like a better algorithm, even if like the tree width is large, if given the promise that we have a nice tree decomposition? Is that what's happening here?
Yeah, you have a good point. There are better algorithms when the tree width is small. Yeah, I should cite those. So yeah, when you have bounded tree width, you can find a nice tree decomposition much quicker. So.
No, but I think the question was, like, the point of this bag thing is that you have a constant size thing you have to play with every turn, right? But now your bags are of size n. So if, for example, if you have an algorithm that's 2 to the size of the width, this is like an everything algorithm.
Right.
So is it really W times n, or is it something better?
I think it should be. I think there should be something better here, like because you're right. If it's W times n, that's not gonna work. But I'll have to check it and get back to you because I don't have it on hand right now.
Sure, no worries.
But you guys are definitely right that if it is actually as stated here, then it's going to be then it's kind of bad. Right, so let's try to design a DP for B matching on these nice tree decompositions. So remember what we're trying to solve, right? We're trying to solve this not just a B matching problem, but we're trying to solve this minimum excess problem, right? So we are given, remember, we're given an imputation X on the vertex set, and we're trying to minimize the excess here over all the possible coalitions. In this case, subsets of vertices, taking X of that set, and we're subtracting the value function of that coalition. In our particular case, nu is the value function for our B matching game, i.e. finding like the maximum weight of a B matching on the induced subgraph. So we need a bit of notation here, and then I'm going to hit you with the big program here. So for any vertex in our tree, I just want to sort of have this description of this sort of a subgraph that's related to that vertex, which is the graph that is induced by all the vertices in bags for that subtree. So if I'm looking at a particular subtree of my original tree that's rooted at I, there's bags associated with all those vertices, and I want to like collect all those vertices together and look at the graph that is induced by those vertices. And I also want to have a quick bit of notation for the edges leaving a vertex in this subtree. It's just the edges. That's exactly what it is. So from a vertex V, delta sub I is the edges leaving adjacent to V, but within that subgraph G sub I. So our subproblems are going to be a little bit more complicated than they were in the weighted voting game case. Our subproblems are going to be indexed by a vertex in our tree. They're going to be indexed by a subset of vertices in the bag for I. They're going to be indexed by a vector, D. It's going to be a vector of degrees. That's why it's called D. And F, which is a subset of the edges inside of that bag. So what this subproblem is saying, like in words, is I want to look at the optimal value of my problem when I restrict my attention to the subgraph GI, and I say that the vertices in X are not going to be matched to anything. If I look at the edges within my bag, BI, I'm taking only those edges into my B matching that are in that set F. And I have this contract on the degrees that say that the degrees are sort of tracked by this vector D. And that's what this is writing out in mathematical notation. So again, if we can solve this, if we can solve these sort of subproblems, then it's not hard to just look at the version of this for the roots and enumerate over all the different possible ways these indices could form for the roots. And that can yield like a dynamic program for the entire problem. Again, since we're working on graphs of bounded Treewidth, these parameters will be of polynomial, sometimes even constant size, if we're just trying to enumerate the number of possibilities there. So that's good. Now, let's see what we do. So when we design this dynamic program, again, I'm going to write it out as a recurrence. And then we can sort of use that intuition we built earlier that connects these recurrence formulas with the hypergraph models by sort of saying like, if the recurrence is enumerating over a certain number of things and those form different edges, I mean, we'll see. I'll get to the concrete thing first. So let's first look at the case of a leaf. Right, so the leaf case is easy. If you're a leaf, then your bag has one vertex. And really all you have to do is figure out, well, one, whether you're taking in that vertex V or not, if you're charging for that vertex. And then otherwise you have to make sure that the contract that you have no degrees and that you're not taking any edges is satisfied. Otherwise you're infeasible. So that one's kind of simple, but introduced vertices are where things start getting interesting. Remember, an introduced vertex, I has a child J, and your bag is composed of the bag for J and the new vertex and a new vertex V. Nice. So yeah, so it looks visually something like this, right? You have this bag BI and you have this smaller bag BJ, and you have this vertex V that's being introduced by the bag B. And so if I want to find a sort of like a minimum excess coalition on the subgraph for GI that pays for these vertices but does not match them to anything, and that obeys these degree constraints and obeys these edge constraints on its matching, then I can look at what happens when I restrict my attention to the bag BJ, right? But I sort of lose information about what's happening at V because the bag for J doesn't have V in it. So I sort of like lose the vertices that were in X, but not in BJ. So really that just means I might be losing like V. And I also, the degrees might shift a little bit because there's some edges touching V here, so I have to shift those in case there are some edges in my matching touching V. And then again, I have to restrict my attention to edges that are in this bag Bj. So I have to remove these edges when I'm looking at that new subproblem. But I also have to pay for everything I removed, and that's what's coming in here, right? I might have to pay for V in one of these ways, and I have to pay for the edges I removed. And then there's two more cases. So there's the forget case, which is a little bit complicated. So in the introduce case, you just have your subproblem directly depends on just one other subproblem. But in the forget case, there are many possible problems it can depend on, because you have this bag. You have I, that's a child J, and the bag I is the bag J, like minus this vertex V. Visually, you have the bag here, and then to get to bag J for its child, you add this vertex V. And then again, there are some edges coming in this subgraph. So what we have to enumerate over when we're trying to solve this subproblem, again, we're trying to solve the minimum excess coalition on the subgraph for I, paying for but not using the vertices in X, and then your matching is obeying these degree and edge constraints. Now you have to think about all the different ways that your solution at I could extend to a solution at J. And that's kind of what we're enumerating over here. We're saying, well, two things can happen, right? Either like our set of vertices that we're paying for but not using, like Y here, either this set is going to be our original set or it's going to add V. So we have to enumerate over those. If we're looking at our new degree contract, D prime, then for all the vertices in BI, it has to obey them. And then for VI, we have new choices. And then, so F, which is our matching that's living inside of BI, it's going to have to extend with some edges to V. And then that's just saying, well, we're going to put that extension in J. And we're going to see what happens. So, and what the cost of our subproblem is going to be, is it's going to be the cost of one of these extensions, but then you got to subtract what was overcounted, right? So the edges in Y here, if you added V, and then the edges in your extension to Fj. So essentially what's happening on a high level is you're looking at the ways you can extend this feasible solution at BI to a feasible solution for Bj. And then you have to like charge yourself for that extension. And then the last case is the join case. So the join case looks like this, right? Your vertex I you're studying has two children, J1 and J2, and your bags are all the same between I, J1, and J2. So essentially in your tree, you have something that looks like this. You have I, and it has two children, and they all have the same bag. And this case was the impetus for generalizing two hypergraphs, because to sort of write the dynamic programs in this case, you need to combine the solutions to two subproblems. And what you're really doing here is you're taking your solutions at the subgraph for J1 and the solutions for the subgraph at J2, and you're gluing them together to form a solution at the subgraph for GI. And that's what this expression is saying. It's because they have the same bags, they're going to obey the same edge contract on F, and they're also going to obey the same contract on the vertices they're not using. There's a possible subtlety here, but I'm going to leave it out. But their degrees, they have to obey this constraint. And what it says is that their degrees have to add up to the degrees requested here for the subproblem at GI. And that can be sort of computed by looking at a vertex, summing their degrees, and then subtracting off where you double counted, which is on the vertices that they share inside of that bag. And over here, we're just subtracting off the stuff we double counted when we glued them together. When we glue them together, we're getting overlap on this bag. And so we have to subtract off what we double counted. The X values in the support of D1 intersect D2 and the weight of the edges in F. And sort of like, this is where like the properties of tree decompositions come in handy, because by the tree decomposition properties, there's no edges in these sets minus the bags. Right. So sort of like in summary, what did we do here? Well, we gave a dynamic program for the minimum access coalition problem on B matchings for graphs of bounded tree width. And because there's this connection between, so there's a two-step thing here, right? Because we did that, we can lift to the congruency constrained version in polynomial with a polynomial sort of expansion. And then because there's this connection between congruency constrained optimization and solving the nucleolus, we can then lift that algorithm to an algorithm for computing the nucleolus, giving an algorithm for computing the nucleolus of B matching games on graphs of bounded tree width for any B, for any weights. And now there was this work by Keibel and Luce that generated this dynamic programming model, that generalized this dynamic programming model of Campbell, Martin, and Rardin, the one we used, to what they called branched polyhedral systems. And there's sort of like this question, like, if we were to take this sort of work to that level of abstraction, would there be any new interesting classes of cooperative games where that work would allow you to compute the nucleolus? So that actually concludes my talk. Thank you everyone for coming and sticking through it. If there are any questions, I'll be happy to take them now. I also appreciate that Ben actually managed to find a helpful reference for this tree decomposition thing, and he posted it in chat. So have a look at that. Otherwise, thank you guys. Thank you everyone.
Right. Yeah, thanks, Justin. So we'll take questions now. If anyone has any questions.
Hello?
Mm-hmm.
Do you want to talk about the Cauchy's lemma on the primes?
Oh yeah. Yeah, if there's no other questions, I can talk about that. Okay. Yeah, I'll just talk about that. So this so let's just remind ourselves what that lemma looked like, right? So everyone can still see okay? Okay, good. So that lemma said, so let's let P be a set of prime numbers. And the size of our P is going to be at least log n factorial. We're going to need n at least 3 here. That's no problem. Then we're going to say that a set of vectors, we're going to call our vectors v1 through vk. And these are going to be 0, 1 vectors in n dimensions. And these vectors are linearly independent over R if and only if there exists some P in P for which V1 to Vk are linearly independent over Fp. Moreover, this set can be found in polynomial time, but we'll just do this part. So let's look at the proof.
Sorry, one thing. Could you take the set of prime numbers to be the minimum of n factorial and k factorial? So it seems like if you have a few vectors over n dimensions, you could just pick a submatrix.
Yeah, I think you could. Yeah, you probably can. Let's look at the proof. I think you can do that. Yeah. So we'll let A be the n by k matrix. So we'll start by considering the n by k matrix whose ith column is this vector vi, right? Now again, like so on one direction, right? If v1 to vk are linearly independent over fp, so we're going to go from that side first over fp. Then we can look at a k by. Then there exists a k by k submatrix. B, we'll call this of A, such that det B is not 0. All right. But then det B is also not 0 over R. Right, so that's kind of the easy direction. The other direction is where we need to put in a bit of work. Now, so we're going to just suppose V1, VK are linearly dependent over R. Over, sorry, not R, over FP, I mean. Right, so let's say they're linearly dependent over FP for all P. Now we have some cases kind of based on the size of K, right? So if K is larger than N, then this is kind of clear, right? Clearly, V1, VK are linearly dependent over R, right? So so suppose, right, K is at most N. So we're going to consider a K by K submatrix of A. And what we want to show is that we will show that the determinant of B is 0. We mean this like over R. So here's a nice observation. For each P and P, P divides the determinant of B because by linear dependence. Note that B is integer, right? Since right, now we're going to use that these things are primes, right? since P are prime, this actually tells us that their product, right? This is the nice thing, right? Their product divides the determinant. Right, so that's pretty good, right? Because then, hence, if that B were not 0, then the product of these primes would be at most the determinant. But then we have this other, but then, right? But that gives us even more problems, right? On the one hand, we can lower bound this to log n factorial. And there's an upper bound because it's the determinant of a 0, 1 matrix, n factorial. And this is, hang on, it's important that this is strict. And that's strict because we only have one prime, which is 2. So this actually yields a contradiction. Hence the determinant of B is 0. So everything is linearly dependent over R. There you go. I mean, kind of pretty.
So, Justin, had another question. So you said that like the complexity of like in the general case as when B is at least 3 for a B matching game, like things become hard.
Right.
Right. So what is known between like 1 and 3? Like what if like the vector is exactly 2?
Right. So for 2, we're somewhere in the middle. So
yeah, somewhere, right.
So for 2, so again, one is polynomial, 3 is believed to be NP hard. But for 2, we really don't know because I've shown with Jochen and Kostya that you can separate over the least car for B equal 2, but there's no hardness associated on that would say that we can't get the nucleolus there. But we're just but none of the techniques from the one-dimensional matching case seem to be extending. This possibility of being able to match multiple partners is really sort of like it's a very like genuine new layer of complexity to the problem.
Any other questions? Right. Yeah, I guess that's the end of the talk then. Thanks everyone for joining. Is there something else you wanted to say, Justin?
Oh, I just wanted to say, I believe Cedric will be speaking next week.
Oh, right. Yeah.
Yeah.
Yeah, Cedric will be giving a talk next week, and believe it's something on like a label correcting algorithm. I'm forgetting the title of the thing, even though I just received it yesterday. Okay. But anyway. So we'll Cedric, we can't hear you. Okay.
Okay.
All right, thanks.
Yeah.
Yeah, I guess. Yeah,
okay,
I guess
yeah.
We'll see them. Yeah.
Yeah, see you all next week. Yeah.
I guess somebody should have asked the more obvious question, which was like,